Minutes after NASA realized what the James Webb Space Telescope had captured inside a black hole, the physics community went into complete chaos. Not because it was a small discovery, not because it was subtle, but because nothing behaved the way anyone expected.
We physicists have waited 100 years since 1916 for this photograph.
Black holes remained largely unknown until the 20th century. A black hole is a region in space where the force of gravity is so strong, not even light can escape.
From the outside, you can't tell what is inside a black hole.
Black holes haunt our universe, dark centers of gravity that swallow everything in their path.
For decades, black holes had been considered the ultimate cosmic dead end. Invisible, untouchable, and theoretically simple. Regions of space where gravity is so intense that nothing, not even light, can escape. Scientists could theorize about them, simulate their effects, even observe the glowing accretion disks at their edges, but no one could look inside. And now, Webb had done something that seemed impossible. In 1916, Albert Einstein formulated the theory of general relativity, redefining our understanding of gravity. In this theory, massive objects warp the fabric of space and time, creating the gravitational pull that keeps planets in orbit and light on its path. Among the equation's many solutions was a startling prediction. Under certain conditions, matter could collapse into a point so dense and compact that its gravity would overwhelm everything around it. Light itself would be trapped, and space-time would fold in on itself. These were black holes. At the time, Einstein himself was skeptical. He believed they were mathematical curiosities, strange consequences of equations rather than real objects that existed in the universe. For 50 years, black holes remained purely theoretical. Astronomers studied stars and galaxies, but no observational evidence existed. Then, in the 1960s, a breakthrough occurred. Observations of X-ray emissions from certain stars revealed anomalies that could only be explained by the presence of an invisible, incredibly massive companion. The star Cygnus X1, orbiting an unseen object that emitted powerful X-rays, became the first strong candidate for a black hole. Suddenly, what had been theoretical was real. Black holes were not just mathematical curiosities, they were cosmic monsters, lurking in the galaxy, shaping the universe in ways we were only beginning to understand. By the 1970s and 80s, our understanding of black holes grew incrementally. Theoretical work on their structure suggested that, at their core, lay a singularity, a point where density becomes infinite and space-time as we know it ceases to exist. Surrounding this singularity is the event horizon, the boundary beyond which nothing returns. Anything crossing that threshold is lost to the universe forever. Black holes were terrifying, mysterious, and unreachable. They were, in a very real sense, nature's ultimate no-go zones. Fast forward to 2019, when the Event Horizon Telescope produced the first direct image of a black hole in the galaxy M87. The result was stunning. A glowing ring of matter circling a perfectly dark void. It was as if the universe had finally allowed humanity a glimpse of something previously forbidden. But even with this image, all we saw was the boundary, the event horizon. The interior, the singularity itself, remained unreachable, a place where our physics broke down entirely. For the first time, we understood that black holes weren't just invisible, they were unknowable. They were a wall that our best theories could not scale. And then, the James Webb Space Telescope entered the scene. Launched to peer deeper into the universe than any telescope before it, Webb was designed to study the earliest galaxies, the formation of stars, and the composition of distant planets. Its infrared sensors allow it to see through clouds of dust and gas, capturing details previously hidden from us. But no one anticipated that Webb would provide the clearest evidence yet of phenomena occurring near, and perhaps even inside, the event horizon of a black hole. Within minutes of processing the data, scientists realized something profound. The patterns of light and radiation Webb had detected did not align with any existing model. The radiation was behaving in ways that could not be explained by general relativity or quantum mechanics alone. In essence, the interior of the black hole was no longer just a theoretical construct. It had become a source of confusion and even unease. Here was evidence that nature itself was defying our expectations. The equations that had guided physics for over a century were inadequate, and for the first time, humanity had concrete reason to admit there was no plan. The discovery was subtle at first glance, but its implications were massive. Scientists found fluctuations in the radiation near the black hole's edge that suggested complex interactions between matter, light, and space-time. Interactions that were not predicted by current physics. Models that had previously been considered robust, simulations that had been run for decades, all failed to replicate the observed behavior. In other words, James Webb had done more than take a picture. It had revealed a phenomenon so strange that it rendered our theoretical frameworks incomplete. This was not just a challenge for astrophysics, it was a challenge for all of physics. For over 100 years, black holes had been a proving ground for theories of gravity, relativity, and quantum mechanics. They were thought to be extreme but predictable. And now, those extremes had become unpredictable. The singularity, the event horizon, the entire interior of the black hole, everything was suddenly more mysterious. Scientists had expected new data, new details, but nothing prepared them for something that outright contradicted what was supposed to happen. Minutes after NASA and the research teams shared the initial results internally, labs across the globe scrambled. The James Webb data was being scrutinized frame by frame, wavelength by wavelength. Supercomputers ran simulations to see if the observed patterns could be explained by previously unknown behaviors of matter or radiation. Theoretical physicists returned to the chalkboard, questioning assumptions that had been considered immutable. In a quiet, almost imperceptible way, the foundation of physics was being tested by a single telescope pointed at a distant black hole. Webb had essentially done something that no other observatory could. It provided a glimpse at the boundary between the known and the unknown, the edge of physical law itself. The discovery was not explosive, not dramatic in a cinematic sense, but it was profound. For the first time, scientists had to confront the possibility that black holes were not just cosmic vacuum cleaners, but phenomena operating under rules we had yet to comprehend. And yet, despite the shock, the work could not stop. Observations continued, calculations were refined, and the subtle patterns in Webb's data were analyzed for any hidden explanation. The consensus among researchers was striking. Something fundamental about our understanding of black holes, and perhaps the universe, had changed. There was no map, no blueprint, no established protocol for interpreting what had just been observed. There was only a stark, undeniable reality. We were witnessing something new, and we had no plan for it. Minutes after scientists began analyzing the James Webb Space Telescope data, the reality of what they were seeing began to sink in. Black holes, once considered ultimate dead ends in physics, were now behaving in ways that were not just unexpected, they were incomprehensible. For decades, scientists had built simulations, ran calculations, and predicted behaviors based on the laws of general relativity and quantum mechanics. But the interior of a black hole, the very heart where matter collapses into the singularity, had always been unreachable until now. The James Webb observations did not directly capture the singularity itself. Nothing can cross the event horizon and survive to report back, but it revealed subtle patterns at the very edge of the black hole. These patterns were not random. They hinted at a structure, a kind of turbulence within the space-time surrounding the event horizon that no one had predicted. Researchers began describing what they saw as a glowing quantum storm, a chaotic region where matter, light, and space-time interact in ways that defy our current understanding. To grasp the significance, it's important to revisit what black holes are supposed to be. Around a singularity lies the event horizon, the point of no return. According to Einstein, once matter crosses this boundary, it is crushed to an infinitely small point, and all known laws of physics cease to operate. Beyond the horizon, time itself slows and space folds in ways that are almost unimaginable. For decades, this singularity was considered a theoretical prediction, a place where equations break down, but nothing could confirm it existed. Now, Webb's data suggested that the event horizon is not a simple boundary. Light and matter near it were interacting in patterns that hinted at hidden complexity. The radiation escaping from the outer edges of the black hole didn't match any of the models created from general relativity alone, nor could it be explained by quantum mechanics, the theory that governs subatomic particles. It was as if the black hole was creating a space where the rules of the universe were bending, or perhaps even breaking. This glowing quantum storm represents more than just turbulence. It may be a sign that black holes are not merely cosmic vacuum cleaners. devouring everything in their path. They could be dynamic laboratories, natural particle accelerators, processing matter and energy in ways that are invisible to us until we have the tools to see them. Some theorists suggest that this turbulence could even encode information about the matter it consumes, a hint towards solving one of the most perplexing problems in physics, the black hole information paradox. The implications are staggering. For years, physicists have debated whether information that falls into a black hole is lost forever. General relativity suggests it is, but quantum mechanics insists information cannot be destroyed. This fundamental conflict has never been resolved. Now, Webb's observations hint at a mechanism, however mysterious, by which information might interact with the black hole's outer layers before disappearing, or perhaps escaping in some form we do not yet understand. Some researchers are already exploring radical ideas inspired by the data. Wormholes, hypothetical shortcuts through space-time, have long been a staple of theoretical physics. While no direct evidence exists, Webb's observations of unexpected light patterns and energy fluctuations have reignited interest in these possibilities. Could the glowing quantum storm be hinting at a naturally occurring bridge through space-time, where matter and energy are processed or even transported elsewhere? Other physicists are turning to string theory for potential explanations. String theory proposes that subatomic particles are actually tiny vibrating strings, and the vibrations of these strings determine the properties of matter and energy. Crucially, string theory requires extra dimensions beyond the familiar 3 of space and 1 of time. These dimensions are normally hidden, but in the extreme environment near a black hole, the effects of extra dimensions could become observable. Some speculate that the turbulence Webb has captured may be the first indirect evidence of these hidden dimensions at work. Even more extraordinary, the glowing quantum storm suggests a form of quantum chaos at scales we never imagined. Normally, quantum effects dominate the microscopic world of atoms and particles. Gravity dominates the cosmic scale. But near a black hole, gravity and quantum mechanics collide, creating conditions where the behavior of matter and light can become chaotic and unpredictable. Webb may have captured this interface for the first time, showing us a glimpse of physics in its most extreme form. Laboratories and supercomputers around the world immediately began running simulations based on the new data. Teams tried to replicate the glowing patterns with known physics, adjusting variables and re-examining assumptions. Every attempt failed. Equations that had been reliable for decades could not reproduce what Webb had observed. Scientists were confronted with a humbling reality. The universe was more complex than the theories that had guided us for over a century. Despite the uncertainty, the discovery offers opportunities. Understanding the glowing quantum storm could unlock insights into the formation of black holes, the behavior of matter under extreme gravity, and even the earliest moments of the universe itself. The interactions between matter, radiation, and space-time near the event horizon could reveal the underlying rules that govern the cosmos, bridging the gap between general relativity and quantum mechanics, something physicists have sought for generations. The first responses to Webb's findings were cautious. Researchers stressed that the data was preliminary, that interpretations must be carefully vetted, and that extraordinary claims require extraordinary evidence. But the patterns were clear enough to spark excitement and intense debate. This was not a minor anomaly. It was a glimpse into a regime of physics that had never before been observed, and it challenged assumptions at the foundation of modern science. Minutes after NASA released the initial analysis internally, theorists began to consider implications that would have sounded impossible even a few years ago. Some speculated that the glowing quantum storm could encode information in ways that suggest black holes are not merely endpoints of matter, but perhaps processors or transmitters of cosmic information. Others proposed that energy fluctuations within the storm might reveal the effects of extra dimensions, the first observable traces of phenomena predicted by string theory. It's a reminder of the limitations of human knowledge. For decades, black holes were thought of as simple mathematical solutions to Einstein's equations. We imagined them as cosmic vacuum cleaners, swallowing everything in their path. But the glowing quantum storm shows that they are far more complex, far more dynamic, and far more mysterious than we ever anticipated. Black holes may not just destroy, they may transform, encode, and interact with the universe in ways that we have yet to comprehend. And yet, even with all this data, many questions remain. We cannot observe the singularity directly. We cannot fully measure the processes occurring within the event horizon. We can only infer from what Webb captures at the boundary. But even these indirect glimpses are enough to rewrite textbooks, to challenge assumptions, and to inspire a new era of theoretical and observational work. Webb's observation of the glowing quantum storm has, in a very real sense, opened a door. We are seeing the edge of physics itself, the boundary between what we know and what we do not. It is a humbling, exhilarating, and unsettling experience, reminding us that the universe still holds secrets far beyond human imagination. For scientists, the challenge is now to understand what these signals mean. For humanity, it is a reminder that even the most familiar cosmic objects can surprise us in ways that defy logic, intuition, and expectation. Minutes after the first analysis, the consensus was undeniable. Black holes are no longer simple endpoints. They are dynamic, complex, and deeply mysterious. Webb has not only shown us what lies at the edge of a black hole, it has revealed that our understanding of reality itself is incomplete. The glowing quantum storm is a signal that the universe still holds secrets we cannot yet explain, and that the next breakthroughs in physics may come not from equations alone, but from daring to observe what the cosmos has been hiding all along. Minutes after NASA and the global scientific community digested the James Webb Space Telescope findings, the implications began to hit with full force. Black holes, long thought to be the ultimate cosmic dead ends, were now something far more complex, far more unpredictable, and far more profound than anyone had realized. The data from Webb suggested not just turbulence at the edge of a black hole, the glowing quantum storm, but something that challenged the very foundations of physics. And for the first time, scientists had to confront the stark reality. There was no plan. For over a century, black holes had been a cornerstone of theoretical physics. They were extreme, yes, but predictable, at least in principle. Einstein's general relativity told us how gravity behaves at cosmic scales. Quantum mechanics explained the microscopic world. And yet, black holes represented a collision between these two pillars, a place where gravity is so intense that time slows, space folds, and matter collapses beyond recognition. Scientists had always assumed that with careful calculation, observation, and theory, the behavior of black holes could eventually be understood. Webb's data suggested otherwise. The patterns of light and radiation escaping from near the event horizon were unlike anything predicted. Matter appeared to interact with the surrounding space in ways that defied both general relativity and quantum mechanics. The glowing quantum storm suggested dynamic processes that could be encoding, transforming, or even emitting information, in direct contradiction to the idea that anything crossing the event horizon is lost forever. In effect, black holes were no longer just destructive. They were active, complex systems whose behavior we barely understood. Scientists immediately turned to theoretical frameworks that had long been considered speculative. String theory, which posits that subatomic particles are vibrating strings moving through hidden dimensions, suddenly became relevant. Could the turbulence and radiation patterns observed by Webb be evidence that extra dimensions were influencing the dynamics of a black hole? Could the interactions we see at the event horizon be a rare glimpse into physics beyond the 4 dimensions we experience daily? These were questions that had previously belonged to thought experiments and mathematical speculation, but now they were grounded in observation. Even more audacious, some physicists began to reconsider the possibility of wormholes or natural cosmic bridges. If the glowing quantum storm was indicative of extreme distortions in space-time, could these regions of turbulence be evidence of structures that allow energy, matter, or information to move in unexpected ways? While still highly speculative, the idea that black holes might be more than cosmic graveyards and instead act as gateways to phenomena beyond our current understanding was suddenly taken seriously. The scientific reaction was intense. Research labs around the globe went into overdrive. Supercomputers ran millions of simulations, adjusting every variable to see if known physics could reproduce Webb's observations. Every attempt failed. Equations that had guided astrophysics for decades were insufficient. Models that had been considered reliable no longer worked at the extreme conditions revealed by Webb. In essence, the universe was telling humanity that its behavior at the edges of black holes is far more complex than our theories could account for. For physicists, this was both exhilarating and terrifying. Exhilarating because the data opened entirely new avenues of research. Terrifying because it highlighted the gaps in our knowledge. Every assumption had to be re-examined. The nature of singularities, the structure of the event horizon, the behavior of matter under extreme gravity, and the relationship between quantum mechanics and general relativity. For the first time in decades, the black hole was not just a theoretical curiosity or an extreme example of known physics. It was a puzzle that could redefine the entire field. One of the most profound consequences is that singularities, once thought to be points of infinite density and the ultimate collapse of matter, may not be singular at all. The glowing quantum storm suggests that processes inside or near the event horizon may prevent complete collapse, or that matter and energy interact in ways that redistribute information instead of annihilating it. If this is correct, the fundamental assumption that black holes are absolute endpoints for matter and information may need to be rewritten. This has implications far beyond the study of black holes themselves. Cosmology, the study of the universe's origin and evolution, relies heavily on understanding extreme gravitational phenomena. If black holes behave differently than expected, it may affect how we model galaxy formation, the behavior of supermassive black holes at galactic centers, and even the earliest moments of the universe after the Big Bang. In other words, the Webb data could impact the entire framework through which we understand reality. Researchers also considered the practical challenges posed by the discovery. Direct observation of black hole interiors is impossible. Probes cannot cross the event horizon and survive. Therefore, all inferences must come from indirect measurements, radiation patterns, gravitational effects, and the behavior of matter near the event horizon. Webb's observations are among the most precise we have ever had, but even so, they are just glimpses. Decoding them requires not only new theoretical frameworks, but also the development of tools and techniques capable of interpreting data from phenomena that fundamentally challenge our current physics. The excitement in the scientific community is matched by a sense of urgency. This is the kind of discovery that could define physics for decades. The patterns seen by Webb suggest that there are processes at work that we do not yet understand, possibly involving new physics, extra dimensions, or interactions between gravity and quantum mechanics that have never been observed. The telescope has given us a view of the universe's most extreme environment, and in doing so, revealed that our understanding of the cosmos is still incomplete. Minutes after NASA released the findings to internal teams, papers and preprints began circulating. Theoretical physicists began proposing new models to account for the glowing quantum storm. Some suggested modifications to general relativity, others proposed mechanisms within quantum gravity, and still others explored entirely new frameworks that could unite both. Every idea was being tested, refined, and challenged. And yet, despite the flurry of activity, one truth became clear. The universe had no regard for our expectations, and black holes had become laboratories for the unknown. It is important to understand that this is not science fiction. These observations are real. The James Webb Space Telescope, humanity's most powerful observatory, has captured evidence of phenomena at the edge of physics itself. It is telling us that black holes are dynamic, complex, and potentially far more informative than we ever imagined. They are not just endpoints. They are active regions where fundamental processes of the universe are revealed. For decades, black holes were mysterious, but at least they were predictable in theory. Now they are unpredictable, challenging, and deeply fascinating. The data from Webb may ultimately help reconcile the conflict between general relativity and quantum mechanics, providing insight into phenomena that have eluded physicists for generations. But that will require years, perhaps decades, of careful work. In the meantime, the most immediate lesson is clear: there is no plan. Humanity has never encountered a phenomenon quite like this, and we are in uncharted territory. The glowing quantum storm is a reminder that the universe operates on its own rules, often beyond our imagination, and that even the most advanced tools cannot fully prepare us for what we might discover. Black holes were once the ultimate cosmic dead end. Now, they are the frontier of physics itself. They may encode information, process matter and energy, and even hint at dimensions and phenomena beyond our perception. The James Webb Space Telescope has opened the first window into this frontier, revealing a universe far stranger and more complex than we had imagined. And as scientists continue to study the data, one fact remains undeniable. The universe does not follow our plans, and black holes are far more than we ever thought they could be.